Welcome to the segment on linkers and makefile. In this segment, we are going to study about how ARM GCC tools can be used to link and make a binary that we can run on a microcontroller. That is our Cortex M4 microcontroller. We will discuss about the mechanism as to how linkers work, how linker scripts are laid out, and what a makefile is and how to write a makefile. So primarily we will be dealing with these three files. Now this is a basic SysTick interrupt code which blinks an LED on the STM32F4 board. We will not be getting into the code as such. We will be getting into the code later in the course, where we'll be going through the same code and we'll be understanding the logic. But the major intention of this particular segment is to see how these source files will be compiled into object files, how those object files are going to be linked, what the object files are compiled into executable and linkable format object files. So these object files will be again having multiple sections, and each section will mean something, and they will again be used by the linker to create the final binary. So there is a lot of information that is packed into the object files after compilation. So as we know, we compile these files individually first, and then we link the outputs of the compiled file. So we are going to see all of that one by one. But just to begin, let us briefly try and understand what the intention is of a linker and a makefile. So first we'll start with the linker. So suppose now we have our three files. So we have our main file, we have say a driver file. So this is a main.c, it's a driver.c. Suppose I'm just giving some arbitrary names to these files. So we have a driver.c, and say we have a file which is called startup.c. Now, generally speaking, those of you who have coded in assembly before, you would say you have coded in assembly on 8-bit controllers, say you have coded on 8051, or you have coded on AVR controllers, or you have coded on some 16-bit processors, say, right? So you would see that the complexity of code will be lesser here. But anyway, maybe the startup segment of these controllers will be much easier than what we are going to discuss here eventually. So all of this, the linking process, the make process, or the compilation, everything is to make our lives easy. So these are tools for us to actually concentrate on the logic of our program, and arranging this code to fit into the memory, and resolving the variables, resolving the function addresses are left to the linker, which otherwise you would have to do yourself. So any program you write is of course will be divided into multiple files for convenience. So it's mainly for convenience and for organization. So you organize the program into understandable and discrete modules logically. So these are like the main.c will be, say, your application layer. Okay, so this is your application, this is your driver. Startup is the initialization layer, and so it's a this is the driver HAL, so this will be a part of the HAL, and things so on and so forth. So basically you are splitting up your program to make it logically feasible, logically understandable. Okay, because writing the program into a monolithic piece of writing a monolithic piece of code is taxing. It is intellectually taxing. It is difficult to write. You have to take care of a lot of things. So generally you don't do it. But in the olden days, program used to be written like this. That is, it is because the machine will only understand instructions and data, and it will start reading the instructions from a particular address, and it just understands binary, and it will probably have some data which again it will fetch and which it will store depending on whatever instructions are here in the instruction segment. Now that's all. It's the way a processor looks into the memory is quite simple if we don't consider paging and caching and things like that. This is a microcontroller. This is the memory layout is quite simple. So this is what happens. So eventually whatever you are doing, even though you logically separate your your application into multiple modules and do whatever, and you write a higher level language, so you write a code in C or do whatever, everything has to be brought down to this format, that is machine for level language format. So eventually it is going to be a series of bytes which will be flashed into a region of the memory. That is what will eventually happen. So you have a choice of, as we discussed, you have a choice of either writing it straight away into the memory, that is creating a file with all the binaries. You just, you hand code the binaries and you just burn it in the memory, or you write it at a higher level and let the compiler take care of converting that into object code, and then the linker take care of resolving symbols, combining all this code into a particular memory area. And we don't have a loader as such here because this is a microcontroller. So linking will stop at creating the binary, and that binary we will need to flash into the controller. That's more or less what happens. So I hope you understand the premise here. So we have 3 files which will actually be combined into one binary. So that is the entire premise of this particular segment. Moving on, like we discussed, this is how a binary looks like. So if this is your memory location, say your memory location starts from 0, and so this is your flash memory. It starts from 0. Not necessarily will flash memory always start from 0. It could be anything. And say it goes on increasing. This is how your binary will be organized. So just bytes. So it will be a bunch of bytes that are flashed into the memory. Now, if we had to, so you have the provision of actually writing code in binary. You could just, open an editor and probably create a binary file straight away. But this is quite not complicated. This is completely illegible. You will not be able to know what is really going on. And probably an expert might be able to do it this way. Somebody who has an immense amount of knowledge in understanding opcodes and so on and so forth. But this is not, it consumes a lot of time. It is prone to errors, mistakes. So this is not advisable absolutely, right? So we will not take this route of actually handwriting the binary code. What we'll do instead is we'll make use of the tools that has been given to us. We will be, of course, using the ARM GCC, GNU GCC tools right through the course. And so this is an open source free toolchain, you can follow along. So you need to try out these exercises. So there is not much exercise here as such, but there will be some commands that we will be issuing to do obj dump and read elf and so on and so forth. And we'll be doing some compilation. We will be writing make files. We'll be writing linkers, scripts. So yes, there is stuff that you can also try out in this chapter. You can write your own linker, make files. You can try out the GCC command. So we will be manually trying out the GCC ARM GCC commands, and then we'll be manually linking it. That is, we'll be manually issuing commands in the first half, and then we will have all those commands automated through a makefile. So now let us look at the compiler and linker flow. This is something that we had spoken of a little while ago, and that is actually shown here with the help of a diagram. So we have some input files like we saw previously, some C and C++ input files, and we have some assembly input files also. We spoke about only 3 files in our example, which we will be seeing, but there could be any number of files. There's no limit to the number of files that you can have. So you have the source code here, and you could also have assembly code going into the compiler and assembler. The job of the compiler and assembler is that when a C source code comes in, the compiler converts that into assembly code first, and then the assembler converts that into object or machine code. So the number of object files that is output here is equal to the sum of all the files that are input here. So it's a sum total of all the files that are input here is equal to the number of object files that you get here. Now something will be becoming clear to you apparently. That is, each file that is compiled as in this stage, it is compiled as a single independent unit. Even though this file may be dependent on a function on this file, at this phase, the compiler does not resolve those addresses. That is, it just say there is a function called in main, which says initialize, say, our PLL. So when you do an initialize PLL, so that call may be made in main. Okay, but when the compiler is inside here in the main.c, suppose, and it encounters the initialize PLL, and it encounters other calls also. At this stage, when its scope is only this file, so it does not really know where the initialize PLL is residing. That is, it does not know the address of the initialize PLL yet. Which file, where it is, which file has that particular function call, it has no knowledge. So it creates an object file. So this main.c creates an object file called main.o. That object file will have a format called elf, and it will have enough information provided to the linker so that when the scope of the linker will be seeing all these files together. So the compiler will be seeing these files one by one, and it will be creating ELF files, and the linker will see that ELF sections inside the object files, and the scope of the linker file is all these files together, and it is going to then at that point in time, whatever function call was made here, it will be a branch to a particular address whenever you make a function call, right? So this will be probably filled with zeros when it passes the compiler phase, because at this stage the compiler really does not know that where this function is residing. It's the job of the linker to actually see the ELF file for this particular file where you have the initialize PLL function actually written. Okay, and from there take that address and put it in here. Now it is more complex than that, of course, but more or less this is the idea. So once it passes through the linker, it joins up all these files, does address correction. That is, all these files, whatever is the compiler and the assembler converts into object files, all of them assume, each of these files will assume that they are starting from memory location 00006. And it goes like that. So every file, second file, again starts from 0 memory location. Third file, that is the object file format. That is how the object file is output. Now, how do you put these files into the flash? You can't, because they are separate files first of all, and the addresses are really not resolved at this stage. So you cannot run the object files on the board. What needs to be done is it needs to be passed through a linker, and the linker will have instructions, memory map specifications given to it, based on which it is going to convert this into an executable file. Okay, the executable file will also again be an object file. Now this object file is going to have everything fixed. All the file contents of all these files will be put into one file with the addresses fixed, and it is going to almost look like the binary file that we saw previously, which we said that is next to impossible, or it's very difficult for us to actually edit by hand. So that is going to be the content of this executable, which the linker is going to give to us. So you see the benefit of having a compiler, assembler, and linker. We write it in human understandable form, and these tools are supposed to be converting it into a machine understandable form. And then we have to pass it through obj copy, because this executable again that you see is going to contain a lot of information, ELF information, headers, sections. You cannot run this .out or .o file directly on the flash. You cannot. Okay, this is in the embedded system. You cannot do that. So what you do is, because this is not a conventional operating system where you just get that .out file and you can use a loader to run it on the processor. You have to use an obj copy command again then. So that obj copy command, it does what? It strips this file, this out file which has come, of all the sections, segments, all the metadata that this file has, and it only keeps the binary, that is the code. So this contains code plus metadata. This only keeps the code here. Once it just keeps the code, that is a string of binary bits, this can in turn be burnt onto the flash. Now when you debug, this executable is necessary, of course, because if a compile is done with a -G option, that is keeping the debug information in the executable, of course we will be needing this .o file, because all the information about the value, say you're tracking a variable, you're tracking a function, if you're tracing something, this binary code only will have the code with, and maybe when you are debugging, you'll know the contents of the registers and the program counter and so on and so forth. So this is going to give you some raw information about where the code is, and what is the program counter, and what are the status of the registers, and so on and so forth. But to convert that back into a human understandable form, that is when you put the code in debug and you'll have that arrow pointing against some line of code and you are able to see the registers in a more beautiful, presentable way, is because this executable has a lot of debug information embedded into it, which can convert that information, that raw information that comes in, and gives it some names. For example, this particular value is actually the value of a variable, and this is a function call, and so on. So this executable is definitely necessary when you are debugging the code. It has a use, just that the flash or the microcontroller will not understand this. This will stay on your computer, this will stay on your operating system, that is the host machine, and there will be when you debug, there will be a connection made between the board and the host machine, and the host machine is going to present you more understandable human readable information based on the debug information here, and whatever is the state of execution on the board, which will be conveyed by the JTAG or the SWD. So the memory map specifier, as we said, is a linker is an intelligent piece of software which actually again arranges the code in a linear fashion, as we discussed. And the memory map specifier is actually, here it means the dot, it is the dot linker file, so .ld. Okay, and the job of the linker file is we call it the .ld, that's the convention, and it will have your complete memory layout of that particular controller, and it will have instructions on which segment where to place which segment in the memory. So you have to instruct the linker with all those commands which it will use to create this executable. So if you have wrong data in the memory map specifier, you are going to get a wrong output, and you are going to get a binary which is not going to run, or it is going to throw some error. It is going to give you wrong output. Okay, so this is the first part. Now, in the first phase of this, we will actually manually issue these commands. That is, we will manually issue ARM GCC commands. We'll manually issue linker commands, and so on. Okay, we'll manually issue these commands, and we'll show that the executable is generated. Right? So, and we'll understand this whole process properly in the upcoming slides. Now, to automate the entire process, now where we just give some command which will actually do the compile, do the linking, and give you a binary which is going to be your final binary. Then you have to introduce yet another software which is called the make. So this diagram remains the same, and you have a make software. So the make is going to, you have something called as a script called as a make file. This can be named anything actually. We'll see that. It's called a make file, and the make software is going to take its instructions from the make file, and the make file will have the names of all the source code and the linker files and so on and so forth. And we will see that we will learn how to write a make file also. And the make file is going to automate this entire pipeline. It is going to automate the compiling and assembling processes. It's going to feed the object files into the linker, and it is going to create the executable. Another output is of the linker is the memory map file. If you when we compile the code, we'll see that we can also get the memory map file as output, which will actually tell us the memory layout of the final output file. So how which section of code goes where is all mentioned in the memory map file. So when you have linked something, say you have linked a piece of code, and if you want to really verify which piece of code has gone where and whether your linker has properly given an output properly, you can check your memory map file, and that is the job of that is how you use the memory map file, probably to verify and check whether the linking process has gone through properly, and of course also to learn the memory layout. For example, if there is somebody who's taking over the project from you, and she needs to know where what the memory layout of this particular application is, then they can have a look at this file and check out how things are. They can do it in two ways. They can look at the memory map specifier, of course, and they can also look at the memory map file, and they will also have to look at the make file. So these are the three things for somebody who's if your project is getting into maintenance mode, and you are making small changes to maybe the source code, you'll have to be aware of your make files, and you'll have to be aware of your memory map specifiers. Say you are porting this code onto a different board which has a different memory layout. Suppose everything is the same. All the peripherals say are the same. All the peripherals work, but the memory, the flash is in a different location. Say the program area is in a different location. Everything else is the same. Suppose maybe your peripherals are in the same location on the different architecture, but your flash is in a different area. The size of the flash is different. Suppose if that happens, then what you need to do is you need to change the memory map specifier. Say you are adding a new feature into the particular application, so you have another file that is added here, which is going to use the standard, all these libraries and so on. And there could be a static library, and it will be using these files only, but it's a separate, say you are adding a driver here. When you add the driver here, what you need to do is you need to come to this makefile, and you have to enter the name of this file, and to make the necessary changes here in the makefile. So say this file is added, but the memory location and other things are the same, which is a more common scenario. You are adding a particular feature here, so you add that name of the new file into the makefile in the appropriate places, and then when you run the compile, you would see that particular file or the particular feature has got added here. Of course, there is testing. This might have bugs, and this might crash your code. So many things can happen, but this is the flow of how the compiler link and the linker is used. In the upcoming slides, we'll actually see how the object files are laid out, what the ELF format is, and we'll see a lot more things, and we'll understand the linking process in great detail.